stranded wire. In the leads wire example, we have simulated a wire with 7 strands. We have specified position of each strand manually. That is doable but takes time. In this example, we have hundreds of strands. Here I will demonstrate how to take into account stranding in an easy-to-implement manner. The assumption I make is that transposition is full and the total current in each conductor is the same. There is no need to distinguish separate strands. We can assign same label and specify total current value in the strand. Well, the task is to calculate Joule losses in the stranded wire and compare with the losses in the solid wire of the same cross-section. The current magnitude is 1 ampere and frequency is 50 kHz. The solenoid is long, so I'm going to simulate only the central part. Okay, let's start QuickField. Here is already defined AC magnetic problem. The frequency is 50 kHz. And let's take a look at the geometry model. Okay, here is the core, and for the core I have specified magnetic permeability and zero electrical conductivity. Then we have the insulation layer here, and we have the air above and around the conductors. And now let's take a close look to the winding. Okay, on the right is solid wire. For these blocks I have specified total current 1 ampere and conductors are connected in series. Electrical conductivity of kappa is 56 megasiemens per meter. Okay. Now what about the stranded wire? There are many strands in the wire and each strand carries the same current. To force this conviction, I specify that strands are connected in series. Of course, in reality they are connected in parallel. I only use this condition to make the current in the strands to be the same. Well, I will get a wrong value of the voltage, but I am not interested in the voltage now. I am interested only in the eddy currents and losses. So I specify current 1 ampere divided by the number of strands. The transposed curved wire features greater length comparing to non-transposed solid wires. So naturally the transposed wire has high DC resistance, about 2%. We take this into account by attenuating the conductivity. Okay. To the left and to the right we will have the same winding, so I utilize the symmetry to reduce the simulation domain. And on the left and on the right I assign symmetry boundary condition with zero tangential field. And in fact this model includes both stranded and solid wires. These parts are independent. There is no connection between the left and right parts. These parts are only placed in the same model side by side, so you can compare the results easily. Okay, now let's take a look at the results. You can see the magnetic flux flows as expected in the core. Now let's zoom in. Here you can see the color map of the current density. It seems there is eddy current only in the solid conductor, but if you zoom in and adjust the scale, you will see that, of course, there is eddy current in a stranded wire too, but the magnitude of this current is much less than in the solid wire. Okay, let's calculate some parameters. I will use the contour tool to calculate flux. Click here to build the contour in the cross-section of the core and follow to the integrals, and this is the magnetic flux. 1.79 millivebers. This is the flux in the coil with the solid wire. Let's remember this value. Copy and paste it here. This is for solid wire. Okay. Contour clear. Now I will select the cross-section of the core in the standard wire solenoid. Again, follow to the integrals, magnetic flux, copy and paste it here. This is stranded. There is no miracle here. We have specified the same current and get the same flux density. But the voltages required to get this current might be quite different. Well, remember, I cannot compare voltages because the connection scheme of the stranded wire is not true, but I can compare currents and losses. Again, I will use the contour tool, but this time I'm going to select the conductor cross section. Click inside, total current 1 ampere as we have specified it, and joule heat losses 47 milliwatts per one turn. Okay. Now let's calculate losses in the stranded conductor. Again, I will use the contour tool, but this time I will draw the contour here. This is faster than selecting individual conductors. Contour close. Now I can calculate total current in this volume. There is no current in the insulation, so I will get only the current in the conductors. Now let's see total current. 1 ampere, same as in the solid wire, and the joule heat losses are 1.8 milliwatts, much lower than in the solid wire. And that is despite the fact that the stranded wire resistivity is higher due to its greater length. But that is for 50 kHz. And if I would like to use stranded wire for 50 Hz, what's then? Let's see. Change the frequency to 50 Hz. Run the analysis again. It took 3 minutes to get the results. Okay, let's take a look at the results. Again, I will use the contour tool to calculate currents and the losses. Integrals, total current 1 ampere, and the joule heat losses are this value. Copy, paste. That was for 50 kilohertz, and this is for 50 hertz solid wire. Now let's calculate losses in the stranded wire. Contour clear. Build the contour around. Contour close. Now total current is 1 ampere, and the joule heat losses are this value. That was for 50 kilohertz, and now this is for 50 hertz. The losses in the solid wire are less than the losses in the stranded wire. Well, of course, the stranded wire features higher resistivity. The conclusion is a stranded wire could reduce losses at high frequency, but it is useless at low frequency. But what is the high frequency value? For example, 1 kilohertz. Should I use stranded or solid wire? Well, open the example in QuickField, change the frequency, run the simulation, and see for yourself. If you search our website for a stranded wire, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and download the simulation files. Simulation files can be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.